Hi, in this presentation we will be demonstrating our final integration of the lab, which is a real-time motor control system built on the STM32 Nucleo L552ZEQ using an RTOS-based design. The goal of this project is to integrate multiple subsystems, including motor control, encoder feedback, user input, LCD display, buzzer feedback, and PIR-based safety, into a single deterministic and safe embedded system. At the high level, this system demonstrates how real-time constraints are handled using structured RTOS task separation rather than a monolithic loop.
For our hardware platform, the main controller is the STM32 Nucleo board, shown on the left side of the image. It runs the control logic, reads inputs, and drives the outputs for our entire system. At the top right is the DC motor, which is the main actuator in the system. Just to the left of the motor is the motor driver, which allows the STM32 to safely control the motor. The motor assembly also includes the encoder, which provides feedback on speed and rotation for closed loop control. At the bottom right, the sliding potentiometer provides an adjustable analog input, such as for setting the motor speed. Next to it, the keypad or touch interface allows user interaction. In the center bottom, the LCD displays system information like speed, target value, and current state. The buzzer provides audible alerts, and the PIR motion sensor is on the right side and detects motion. Finally, the status LEDs are the three onboard LEDs on the STM32 board itself near the top left of the image.
At the system level, the application operates in four conditions: stop, clockwise, counterclockwise, and emergency. It's important to clarify that emergency is implemented as a supervisory lockout condition layered on top of stop rather than a direct enum state. The motor control policy is hierarchical. The keypad selects the operating state and direction, the potentiometer defines the speed. There are three important constraints. The motor never starts unless a valid motion state is selected. The potentiometer alone cannot start the motor. A zero potentiometer input forces zero speed even if direction is selected. This ensures safe and predictable behavior. To support this behavior, we structured the system using an RTOS. The system is implemented using an RTOS with four main tasks. The safety task runs at the highest priority and handles PIR detection, emergency activation, and rearming. The motor task runs a control loop every 10 milliseconds, computes target RPM, and updates PWM. The encoder task periodically calculates actual RPM from pulse counts. The UI task handles user inputs, LCD updates, LEDs, and buzzer logic. This priority structure ensures that safety-critical logic always preempts lower priority tasks. Interrupts are kept very short. The only capture events and signal tasks using flags or queues. All non-trivial processing is deferred to tasks, which improves determinism and reduces jitter. This aligns with real-time design principles where responsiveness and predictability are critical.
So the system was built incrementally. First, basic stop, clockwise, and counterclockwise control was implemented. Then PWM-based speed control was added. Then encoder feedback was integrated for closed loop behavior. The LCD and user interface were then added, and then buzzer feedback was implemented for confirmation. Finally, PIR-based emergency logic and secure rearming was integrated. This modular approach ensured that each subsystem could be tested independently before full integration. I'll now explain the safety mechanism and feedback strategy. When the PIR detects motion for a sustained period, the system enters an emergency condition. At that point, the motor is immediately stopped, PWM is forced to zero, normal commands are ignored, the buzzer enters an alarm mode, and the LCD displays an emergency message. Rearming requires deliberate user action and only occurs once motion is no longer present. All feedback, LCD updates and buzzer, is handled in a non-blocking way inside the UI task, ensuring the system remains responsive. Now we'll move on to the live demonstration.